So a common situation in high school physics is when you have a conducting bar that's part of a circuit dropped in a magnetic field. So I have a conducting bar here of a known mass and length, and it's going to be released from rest in a magnetic field that is directed into the page. There's a couple of things to figure out here. First, I'll find the direction of the current in the resistor at the top of the loop. I'll find the terminal velocity of the bar as it falls. And finally, if the bar is falling at a known velocity, I'm going to derive an expression for the rate at which heat is being dissipated in the resistor as the bar falls down the rails. For part A, I want to figure out which way the induced current is going. According to Faraday's law, a change in magnetic flux through a circuit creates an induced EMF, or an induced electromotive force. This electromotive force is going to create an induced current in the circuit, which will pass through the bar and through the resistor. And then the negative sign in this equation gives Lenz's law, which states that the direction of the induced current is going to be such that it opposes the change in the magnetic flux. And this induced current is going to generate its own magnetic field that tries to stop the flux from changing. So here the field is into the page, which means the flux is also into the page. As the bar falls, the area enclosed by the loop containing the bar and the resistor is increasing. And then since flux is magnetic field times area, that means the flux is increasing. To stop the flux from increasing, I would want an induced current to create a field to oppose this. So that would mean the induced field is going to be out of the page. So to get an induced current to create that field, I use the right-hand rule, which says I'll point my thumb out of the page to resist the change in flux. Again, the flux is into the page and increasing. I want to act against that, so I point my thumb out of the page. And when I do that, my fingers are going to curl counterclockwise, which means that current's going counterclockwise through this loop and going left through the resistor. Next, I want to find an expression in terms of the given variables for the terminal velocity of the bar. Now, because there is a current flowing through the bar, that current's going to mean there's a magnetic force on the bar as it falls. The direction of that force is given by another right-hand rule. So if I have a wire or a bar with current flowing through it, I can use the right-hand rule where I point my thumb in the direction of the current, my fingers in the direction of the field, and then my palm would be facing in the direction of the magnetic force. So in this case, where the field is into the page and velocity of the charges through the bar or the current are to the right, if I point my hand, the palm in that case would be pointing up, so the magnetic force here is also directed upwards. Whenever there is an induced magnetic force in this type of situation, it's always going to be a resistive force. Newton's second law says that the net force on the bar equals mass times acceleration for the bar. And if I take the direction of motion as positive, I have a force in the direction of motion, which is gravity, mg, the weight of the bar, minus the upwards magnetic force on the bar. And in this case, for the force, I'm going to use the magnetic field magnitude times the current in the bar times the length of the bar, or Bill, which is the magnetic force. For the current here, I can use Ohm's law, which says that the voltage, which in this case is the induced EMF, equals current times resistance. And I can rewrite my equation like that, where current is induced EMF over resistance. And the epsilon value here is the induced EMF in a bar moving in a magnetic field, which there is a formula for. So it can be derived that the induced EMF in a bar moving in a field is given by the velocity of the bar times the magnetic field magnitude times the length of the bar. So I can substitute that in. And now I'm looking at the net force at terminal velocity. And then as the bar falls, the magnetic force will get bigger. This is the expression for magnetic force. It is based on the velocity of the bar. So it's going to start off at rest, so there will be no magnetic force. But then as it accelerates due to gravity, it's going to gain velocity, which means it'll gain magnetic force, until the magnetic force equals the gravitational force. In that case, the net force is 0. And then if there's no force, there's no acceleration. So I have a constant or terminal velocity. So I'll set the net force equal to 0. In that case, I'm trying to solve for this variable here, Vt, which stands for terminal velocity. And when I rearrange this expression, I get that terminal velocity is mrg over b squared L squared. Because of the resistive magnetic force, not all the bar's potential energy is going to convert into kinetic energy. Some will be lost as heat, So this part asks for the rate at which heat is being dissipated in the resistor, or the power in the resistor, when the bar is falling at a given velocity v. So for any element in a circuit, the power is given by the voltage in that element times current. And then Ohm's law, which says that V equals IR, I can substitute IR in for the voltage, and I get that the power is the I squared times R. And then the current here is the induced EMF over R, and I said earlier that induced EMF is BLV, where V is the velocity it's falling at a given time. And then if I simplify this, I get the power is B squared L squared V squared over R.